بسم الله والصلاة والسلام على رسول الله وعلى آله وصحبه ومن والاه. Maintenance of skeletal muscle, mitochondria, and health, exercise, and aging group 4. Introduction. One of the most dramatic physiological alterations in living cells responding to an external stress or is the acceleration of mitochondrial respiration associated with change in original dynamics. Rearrangements in mitochondrial morphology that accompany this increased functionality are designed to facilitate the diffusion of foodstuff, substrates, and O2. The cellular response to exercise improves the intonation of internal signaling cascades that provoke an altered gene expression response, leading to augmented original biogenesis and the simultaneous activation of mitochondrial autophagy, mitophagy, with the purpose of increasing original turnover. When muscle is induced to respond repeatedly to increase energy limits of acute exercise over the course of many months and years, the tissue adapts to produce more mitochondria with higher density of ETCs, setting remarkable example of tissue plasticity in the face of energetic stress. Mitochondrial morphology in muscle. Skeletal muscle mitochondria exert an interconnected network, often referred to as reticulum, depending on their location within the muscle fiber. Below the sarcolemmal membrane, proximal to capillary and nuclear, reside the subsarcolemmal SS mitochondria, which are important in providing ATP for membrane-active transport as well as for gene transcription. The second subfraction of mitochondria lies between the myofibrils adjacent to the Z line, and they are termed intermyofibrillar IMF mitochondria. They play a prominent role in providing ATP to the contractile filaments and are in direct contact with the transverse tubules. Thus, they play an important role in calcium plus 2 signaling. SS and IMF mitochondria also have distinct morphological characteristics that are evident when viewed with electron microscope images. Specifically, SS mitochondria appear more connected, whereas AMF mitochondria are much more elongated as they extend between the myofibers. The effect of exercise disuse and disease. Mitochondria can adapt to change in energy requirements of cell by adjusting their Z and distribution. The adaptations observed with regular exercise training shift the muscle mitochondria morphology profile toward that of a density within mitochondria of long-term trained athletes. In other case of disuse and or aging, the fragmented mitochondria reticulum is accompanied with reduction in mitochondrial volume, impaired respiration, and elevated reactive oxygen species ROS emission. Biochemical and functional changes in mitochondria as a result of exercise. More recently, a number of mitochondrial markers have been employed by many research groups to estimate mitochondrial adaptations to chronic exercise, such as cardiolipin content IM, phospholipid citrate synthase CS, carbas cycle enzyme, succinate dehydrogenase complex 2, and per-or cytochrome C oxidase COX complex 3 to complex 4 to represent genes in overall mitochondrial content. More work has subsequently investigated the effect of various training modalities and has consistently demonstrated that exercise promotes an increase in the respiratory capacity during beta oxidation, as well as maximal oxidative phosphorylation and ETC capacity independent of mitochondrial content. In addition, chronic exercise training results in education of ROS emission during acute exercise, indicating particular regulation of the ETS in trained muscle.